Okay, example 2. Find the critical numbers of f of z equals z plus 2 over z squared plus 2z plus 5. Again, we have a 3-step checklist. 1, 2, 3. I'd recommend, even if you don't write down what 1, 2, and 3 represent, as long as you write 1, 2, 3 down on your paper, it'll be enough to jog your memory. Oh yeah, I'm supposed to check 3 things. And if you practice it enough, you know what those 3 things are all the time. Derivative equals 0, derivative is undefined, and endpoints. How many endpoints are there here? Remember the problems we had yesterday? Looks like that. Or it might have said 0 less than or equal to x less than or equal to 3. I should put brackets here. Right? 0 and 3 would be critical numbers for this one. Endpoints can be important. Okay? If it was the parentheses part, 0 and 3 wouldn't count because they're missing value endpoints, right? And they don't exist. So, but if it has equals to on them, endpoints do matter. All right? You should graph them anyway. I suppose they can still be called critical numbers. You should graph them anyway because they're the end of the graph, open circles instead of closed circles. But yeah, just keep that in mind. First derivative is required for these two, so we're going to differentiate. I see a quotient, so I'm going to do f prime of z and apply the quotient rule. So low d high is going to be z squared plus 2z plus 5. D high is going to be 1 minus high z plus 2. D low, which is going to be 2z plus 2. Over the square of what's below, which is going to be z squared plus 2z plus 5, the quantity squared. Alright, let me just have a little bit of a challenge to you guys, because going back to last chapter, the main issue you guys had with doing these quotient rule problems was your algebra. From this point forward, you got the derivative correct, you did all the calculus right, but then all of a sudden your brain really went dead to algebra. So let's just focus on some stuff here. The red stuff's being multiplied together, and the product of the red things is being subtracted. The product of the red things is going to be more than one object, so when we multiply the red stuff together, we're going to have to distribute a minus sign through. Okay? So what that requires me to do when I multiply the red stuff together, 2z squared, outside 2z, inside 4z is going to be plus 6z. Last times last is plus 4. That's what the product of those two things is. That's being subtracted. These parentheses here are necessary, because z plus 2 times 2z plus 2 is a product of binomials that's being subtracted. The product is being subtracted, so that means the entire contents of the product, every piece of that product has to be subtracted. Okay? Parentheses are necessary when they are, and some of you aren't being very diligent about that. So again, this is being subtracted, this whole product, so the entire product in parentheses has to be subtracted. As far as the green thing is concerned, a positive times the product, parentheses aren't necessary. So z squared plus 2z plus 5 is what the product of 1 and z squared plus 2z plus 5 is. If you wanted to put parentheses around that, that wouldn't hurt, but it's not required in that sense because nothing's happening to that. This thing is being subtracted by all this stuff. This thing is not being subtracted itself, so as soon as I multiply 1 times all that stuff, it's now fixed. Okay, but with the red one, I do have to distribute a minus sign through. The other thing is that denominator is part of the derivative. It has to come along for the ride here. So make sure that you are keeping that along, and then f prime of z is the notation we're using for that, so we're going to keep it f prime of z. Final step of this, if I distribute that through and combine like terms, if I can do that all in one step here, I think we can handle that. I've got a z squared minus a 2z squared, minus that, right? So it's going to be negative z squared. And then I've got a plus 2z being subtracted by a 6z, right? Minus 6z plus 2z is going to be minus 4z. And I have a plus 5 being subtracted by plus 4, so 5 minus 4 is going to be plus 1. All over z squared plus 2z plus 5, the quantity squared. Okay? This is what's called a rational function, right up here. Rational functions have asymptotes sometimes. Vertical asymptotes, values where x is not allowed to exist. How do we find vertical asymptotes? set the bottom equal to 0. Division by 0 creates vertical asymptotes. Z squared plus 2z plus 5. Try this out. So if I go back to my quadratic formula program and type in my z squared plus 2z plus 5, hit enter, notice we get imaginary answers. All that means is it doesn't equal 0. Okay. In calculus, we don't graph imaginaries, we graph reals. So if we get imaginaries, that means they don't exist. There's no division by 0. Okay, notice that the denominator of the original function that would create the asymptotes is also the same as the denominator of the derivative, except it's squared instead of the first power. If this can't equal 0, this can't equal 0, so 0 squared is never going to happen, so it's never going to be divided by 0, which means it is never undefined. If that were equal to 0, then this would be equal to 0. Those values will be critical numbers. Something happens there. What happens there is a vertical asymptote. And important things happen. High points, low points, asymptotes, all kinds of stuff like that happens. So again, all you're doing with calculus here is you're compiling a list of values that are important where things might happen that are just not just basic. Boring, 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 boring. Hey, it turned. That's important. Okay? Boring, boring, boring. Hey, look, it goes up to infinity, asymptote. That's important. Okay, that's all calculus is doing there. It's pinpointing specific values where important things occur. Okay, as far as number 1 is concerned, a rational function equals 0 if the top equals 0. So if the top equals 0, I'm going to get 0 over something. And if 0 over something happens here and the first derivative equals 0, what does that look like? First derivative is 0, which makes a slope of 0, which makes a, wow, already said it 3 times today, horizontal line. If the slope equals 0, if the top equals 0, 0 divided by number is 0, right? We already know the bottom's never going to equal 0, so 0 divided by a number that isn't 0 equals 0. F prime of z represents slope. If the slope equals 0, we get a horizontal line. If we get a horizontal slope, the graph hits a high point or the graph hits a low point. So again, that's all 1's ever telling us, is where the slope equals 0, where a horizontal slope occurs, where the graph may or may not hit a high point or a low point, or it may again just flatten out and go back up. One of those 3 things is going to happen if f prime of z equals 0. I just want to know the z value where it occurs. And again, looking at the top, look, the top is just a quadratic function. So if I just do the quadratic formula on negative z squared minus 4z plus 1, negative 1z squared minus 4z plus 1 comes out to at negative 4.24 and positive 0.24. The last problem I went 4 decimal places, actually 2 decimal places is quite sufficient. We're graphing, and if I go 4 decimal places, my estimated spot on that graph is not going to be any different than if I go 2. So those 2 values of z are the ones that matter. Those are the ones where bottoms or tops of the graph are going to occur. Okay, and again, that's all you have to do for today. Where does the derivative equal 0? Right there. Where is it undefined? Never. Where is it an endpoint? Never. So there's your answers. There's my critical numbers. Again, if we want to compare that to the actual graph itself, again, this is for my instructional purposes only. You don't have to do this tonight. If it says find critical numbers, just find critical numbers. If it says graph, then you graph x squared plus 2x plus 5. I'm going to go from negative 5 up to 1. Let's go negative 10 to 10. Let's see what happens. All right. So, let me change that a little bit. I'm going to go from negative 1 to 1 on the y-axis. And let me just scoot this out a little bit more too. Let's go from negative 7 to 3. Just to get a better look at it. It's going down and it starts going back up. It keeps going back up and it starts going back down. And 1, 2, 3, 4.24 is the bottom, about 0.24 is the top. Horizontal slope, horizontal slope. And that's all you're finding here. You're finding where those things happen. Those are important things for us to look for. That will help us to establish specific critical numbers. These are x values we want to pick for this graph. that would get you a bottom and a top point. And again, as we continue in chapter 4, we're going to use second derivatives to find some critical numbers also, and they're going to tell us other things. Instead of tops and bottoms, they tell us other things. So we're going to find 5, 6, maybe 10 important points that want to be graphed, pick a few more points, and then all of a sudden you got this pretty detailed graph for just a few points.